Hello everyone, welcome back to my channel. As you all know, this is Shrujana graduating in Sri Venkateshwara College of Engineering, Bangalore, SEM 2 and Section Infinity Branch ECE subject Mathematics. And today's topic is about image processing. Introduction to image processing. Image processing is the analysis and manipulation of images using algorithms. That involves enhancing images to exact useful information or improve visual quality. Applications of image processing include medical imaging, satellite imaging, and facial imaging. Types of image processing. Type enhancement techniques improve the visual quality of an image by adjusting brightness, contrast, and sharpness. Image resortation methods aim to recover the original image from the degraded version caused by noise or blurriness. Image segmentation priorities an image into regions to simplify analysis and processing tasks. Image processing algorithms. Edge detection algorithms identify edges in an image by detecting changes in intensity. Histogram equalization adjusts the distribution of pixel intensities to improve contrast. Convolution renewal networks are used for tasks like image classification and object detection. Image compression. Image compression reduces the size of an image file while preserving visual quality. Lossless compression methods retain all image data without loss. Lossy compression techniques sacrifice some image quality for significantly smaller file sizes. Image filtering. Spatial domain filters operate directly on the pixels of an image. Frequency domain filters manipulate the frequency components of an image using techniques like Fourier transforms. Common filters include Gaussian, median, and Sobel filters for tasks like noise reduction and edge detection. Here in the picture, you can see 2D Fourier transform, example 3, and image recognition. Image recognition involves identifying objects or patterns in images. Deep learning techniques such as convolutional neural networks have revolutionized image recognition tasks. Applications of image recognition include autonomous vehicles, medical diagnosis, and security systems. Image segmentation. Image segmentation divides an image into meaningful regions or objects for analysis. Techniques like thresholding, clustering, and edge-based segmentation are commonly used. Segmentation is crucial for tasks like medical image analysis, object tracking, and image-based measurements. Image registration. Image registration aligns multiple images of the same scene to enable compression or fusion. Technical include feature-based recognition, intensity-based recognition, and deformable recognition. Recognition is essential in applications like medical, imaging, remote sensing, and imaging mosaicism. Here you can see the some of examples how the image and image decomposition, image feature, DBF, fuel pole, DBF, image feature, and image decomposition. Image analysis. Image analysis involves extracting quantitative information from images for decision making. Tasks include feature extraction, pattern recognition, and object measurement. Image analysis is used in fields like remote sensing, quality control, and biometrics. Future trends in image processing. Emerging trends in image processing include explainable AI for transparent decision making, generative adversarial networks (GANs) are being used for tasks like image synthesis and style transfer. Advances in hardware such as GPUs and TPUs are enable faster and more complex image processing tasks. And the next and the subtopic, vector space and linear transformation. Introduction to vector space. A vector space is a set of vectors that are closed under addition and scalar multiplication. It is defined by a set of elements called vectors and two operations, vector addition and scalar multiplication. Vectors in a vector space must satisfy certain properties such as commutativity, associativity, and distributivity. Properties of vector spaces. Vector spaces must have a zero vector denoted by 0, which is the additive identity. Each vector in a vector space must have an additive inverse, ensuring closure under addition. Scalar multiplication in a vector space must be distributive over addition of vectors. Subspaces and vector spaces. A subspace of a vector space is a subset of vectors that form a vector space themselves. Subspaces must contain the zero vector and be closed under vector addition and scalar multiplication. Subspaces can be defined by the span of a set of vectors or as a solution space of a system of linear equations. Linear transformations. The linear transformation is a function between two vector spaces that preserves vector addition and scalar multiplication. Linear transformations map vector from one vector space to another while maintaining the linear structure. Examples of linear transformations include rotations, reflections, and scaling operations. Kernel and image of linear transformation. The kernel of a linear transformation is a set of vectors that map to the zero vector. The image of the line transformation is a set of all possible outputs of the transformation. The rank mutuality theorem relates the dimensions of the kernel and image of the linear transformation. Matrix representation of linear transformations. Linear transformations can be represented by matrices through their action on basis vector. The columns of matrix represents the image of the basis vector under the transformation. Matrix multiplication with the vector corresponds to applying the linear transformation to that vector. Eigenvalues and eigenvectors. Eigenvalues are scalars that scale eigenvectors while multiplied by the linear transformation. Eigenvectors are non-zero vectors that remain in the same direction after being transformed. Eigenvalues and eigenvectors provide insights into the behavior of the linear transformations. Applications of linear transformations. Linear transformations are fundamentals in fields such as computer graphics, image processing, and quantum mechanics. They are used for geometric transformations, data compression, and solving systems of linear equations. Understanding linear transformations is essential for various mathematical and computational applications. Conclusion. Vector spaces and linear transformations are foundational concepts in mathematics with broad applications. They provide a framework for studying geometric and algebraic structures in an unified way. Mastering vector spaces and linear transformations is crucial for advancing in fields like linear algebra, physics, and engineering. So this is all about this today's topic. So if you like my video, please like, share, and subscribe. Thank you.